Again, the first problem was the example that we had in last class, worked out again, that you had a sample from the Bernoulli. The MLE is still there. We worked this out last semester. The expected value is that. The variance is larger than or equal to that. We computed the Fisher information last class. And we can see that the variance in this case is equal to that, which is equal to the Fisher information. So this is an efficient estimator. And in problem number 2, which is problem 6.2.1 of your book, you have a random sample from the normal distribution with fixed known variance. We compute, and the question has to show that X bar is an efficient estimator of theta. So the expected value is theta, so it's unbiased. Therefore, same as in the previous problem, K of theta is going to be theta, so K prime is 1. We compute the Fisher information using the formula. I claim that the regularity conditions 0 through 5 are satisfied here, so we can use this formula to compute it. So we do so, and we get that the Fisher information is 1 over sigma squared. Then you compute the variance of the estimator that is given. In this case, it is known X bar. We've been dealing with this, so the variance of X bar is sigma squared over n. And then you take now 1 over n, I of theta, what is it? You compute, you see it's exactly equal to that. Therefore, the variance is equal to the Rao-Cramer lower bound. This is the Rao-Cramer lower bound. And when that is the case, you say that the estimator is an unbiased estimator. That's it. That's all we did last time. And that was a review of that. Now let's look at the other problem that I have. So the next problem is it's giving you a distribution, and I want you to try this with first. It's kind of repeating the same steps. So we have a distribution 1 over theta for 0 less than x less than theta. This is technically the uniform distribution on the interval from 0 to theta. That's what it means. And the condition is given that theta is positive. And we say formally compute the reciprocal of n expected value of d natural log over d theta f of x theta squared. So it says formally compute this and then compare with variance of n plus 1 over n yn, where yn is the largest observation of a sample of size n. So now the random variable we need to compute and to compare it to is n plus 1 over nyn. So we need to do the whole work that we just did on the previous example, but do that on this example, computing this is actually the feature information. So this is the definition of the feature information. When you multiply by n, you get n times I of theta, which is the denominator of the Rao-Cramer lower bound. So let's try that and give. That'll be a pretty easy thing here. So what is this n expected value equal to?
N by theta square.
First of all, natural log, you take natural log of this, you get negative ln of theta, right?
Yeah.
You take the derivative, you get
Minus 1 by theta.
over theta. So this is gonna be expected value of minus 1 over theta squared, right?
Yeah.
So there's really nothing, no work to do there. And that's 1 over theta squared, so it's n over theta squared. And so that implies that 1 over that thing is nothing but theta squared over n. So that's the first step of the answer. In the second step of this answer, because they want you to compare this thing to the variance of the n plus 1 over nyn, where yn is the largest observation, you want perhaps to be able to find the variance of n plus 1 over n yn. How do you find that? Well, first of all, you gotta remember what the distribution is equal to. Find that distribution and then from it find its variance. So in this case, yn is defined as being the largest observation. So it's maximum of x1, xn. So what's the distribution of yn equal to?
0.5 n by n plus 1. Oh, 1 by theta.
Wait a second. So how do we find the distribution of the largest observation?
So it's a base case theta equals 1.
That's f x of x raised to the power n. This is from 575. The distribution of the largest observation is the distribution of the family, the population raised to the power n. And so here, that implies that the density, little Fyn of x is n little fx of x times fx of little x raised to the power n minus 1. And the population, this is 1 over theta, that's uniform. F of x in this case is x over theta. So that is n times 1 over theta times x over theta raised to the power n minus 1 with x between 0 and 1 and theta. So that's the density, which means that the mean of yn is integral from 0 to theta of n x over theta times x over theta to the n minus 1 dx. That is obtained by multiplying the density by the variable and integrate. So when you do this, what you get? So this is integral from 0 to 1. If I set x over theta,
Why is it integral of n times x over theta? Should that be 1 over theta?
the mean, how do we compute the mean? To
Oh,
multiply.
no, she meant x by theta, and she was asking which 1 by theta.
That's the question I'm answering. So how do we compute the mean? We multiply the density by x. That's the density. You multiply by x. That's x over theta. That's it here.
Okay.
Now here, when you do the change of variable, this is x over theta, x over theta. So that becomes x over theta to the n minus 1. And if I want to do the change of variable, putting x over theta as a new variable, I would have an extra theta that is needed because this dx doesn't have its own theta. So that's going to be n t to the power n minus 1 times the t also here. So that's n times t to the n dt, where t is x over theta. So when you do this, that's what you get. And so you get that the expected value is, when you integrate this, you're getting theta n over n plus 1. And that's the reason why you get the expected value of n plus 1 over n times yn is equal to theta. So this is really an unbiased estimator. And because it is an unbiased estimator of theta, that also means that k of theta in this example is going to be equal to theta. So k prime is 1, and therefore the Fisher information, the Rao-Cramer lower bound is just going to be 1 over n times the Fisher information. Now, last thing to do here is find the variance, right? So to find the variance, you might want to compute the expected value of yn squared. What is the expected value of yn squared going to be equal to? It's this same thing, just that you're going to have x squared there. So integral 0 to theta and x squared over theta, and then x over theta raised to the power n minus 1 dx. We can do the same change of variable. To do that change of variable in this case, you need an extra theta here. To make this also theta squared, you need an extra theta here to have dx over theta. So you need theta square out. Integral from 0 to 1. And now you have n, and then t raised to the power n minus 1 plus 2. So that's n plus 1 dt. And when you integrate this thing, that's going to be n over n plus 2. So you get theta square n over n plus 2.
Oh, we can break that and integrate as well, right?
What's that?
If we want, we can sum those powers and take out the constants and integrate as well.
I don't get what you're saying.
Oh, I meant summing up x by theta square times x by theta n plus 1, and then taking out everything that's not x and then integrating.
Why do I need to make life miserable for myself?
Okay. Okay.
If you do that, you're going to continue multiplying the thetas, taking out, and then when you finish integrating, plug in theta, and then cancel whatever. And all of that is gone here when I do the change of variable right away.
Yeah.
So when you do the change of variable, t equal x over theta. When x is theta, t is 1. That's why you get 0 to 1. When x is 0, t is 0. So you're integrating 0 to 1 and everything is gone.
Yeah.
If you try to do what you're saying, you might still get the same answer after spending 10 more minutes.
Yeah.
All right, so we got the square here, and because you got that, what happens in this case? Is the computation here correct? Do you agree with this?
Yeah.
Now, the variance of yn is nothing but expected value of yn squared minus expected value of yn squared, and that's going to be theta square n over n plus 2 minus, and this is going to be theta square n squared over n plus 1 squared. Okay, so we can simplify this. That gives you n plus 1 squared times n, and here you have n squared times n plus 2. Things are going to cancel up there, so that's theta squared times, here you're going to have n cubed plus 2n squared plus n minus n cubed minus 2n squared divided by n plus 2 n plus 1 squared. As you can see, as I said, things cancel. So you get theta squared times n over n plus 1 squared times n plus 2. From which you can find that the variance of n plus 1 over n yn. How do we find the variance of this thing if we know that it's equal to n plus 1 over n squared times variance of yn? And when you do that, the n plus 1 square cancels. N square and n, they cancel. You have n at the bottom, so you end up with theta squared over n times n plus 2. So this is the variance of n plus 1 over n times yn. And the question was to compare this variance to the lower bound, which is computed here as n over to the inverse of the lower bound, which is here theta squared over n. Which of these two things is smaller, this or this?
The one we freshly calculated is smaller.
So this is smaller, right?
Yeah.
Does it make sense? The comparison says the variance of n plus 1 over n, yn, is larger, is less than, strictly less than.
Can you raise up the paper?
This variance is strictly less than 1 over n I of theta. What does it mean? Does it make sense? What does the theorem that we are using today say?
Now there's the derivative of k theta, and we square it on the top. Maybe that is very small, clipping the symbol.
That's not a reason. So the theorem that we are using here today states what? That the variance of any estimator is larger than k prime of theta square over ni of theta, with k prime equals, in this case, to 1. So that theorem states exactly the opposite of what is written here. Why? That's the question. Does it make sense? Can we have such a result? Which means, can we have a variance that is smaller than the Rao-Kramer lower bound? And if there is no mistake in our work and we did everything correctly, why do you think this would happen, though the theorem is stating that it cannot happen? I can't hear you, Tiffany. Seems you're talking, but your microphone is muted.
Sorry, I was telling my 10-year-old it was okay.
Oh, all right, sir. I thought you were answering the question. So any idea?
It means that it's not an efficient estimator, right?
Technically, it means it's even better than an efficient estimator, which is something that can never happen. So, and the question is, why are we having this if we are agreeing that the computations are correct? Shukurat, we are used to having cameras on when we are taking these things online and participate in the class.
Dr. Longla?
Yes.
Although it doesn't matter, right? I think the variance of n plus 1 by n equals to you wrote n instead of n plus 1. At the end, you wrote n and n plus 2, but shouldn't it be n plus 1 times n plus 2?
What do you mean?
On the second line, you are multiplying. No, below that.
Here?
If you look at that and then the one below that.
Here?
Yeah, shouldn't that be n plus 1 times n plus 2?
I took that variance multiplied by n plus 1 over n squared. That's what you get.
Oh, okay. Yeah, the variance formula. Okay. Okay.
The problem is not in the computation. I can guarantee you the computations are correct. But why do we have this inequality that doesn't follow the usual way? And the thing is, you need to go back to the assumptions to understand what the problem is. The theorem comes with regularity conditions, which means if you don't check those conditions and you just start saying, hey, the Rao-Kramer lower bound is, then you're fooling yourself. You need to make sure you always check those assumptions before using it. What do they say? One of the conditions is that the support of the distribution is same for all values of theta. That's one of the conditions. And when you look here, this distribution has support 0, less than x, less than theta. So when theta changes, the support changes. So these random variables don't have the same support for different values of theta. The support is this. The support is the set of all values of x for which the distribution is not equal to 0. And it is not the same for all values of theta, because when you fix theta, everything after theta, the density is 0. So this makes sure that this problem does not fall under the umbrella of the problems where you use that formula to state that the variance of an estimator is going to be larger than 1 over ni of theta. The conditions of that theorem are not satisfied in this case. That's a reason why you could find a variance that is smaller than the Rao-Kramer lower bound. And so you need to always be very careful when you're using those things. That's the reason why we were doing this problem. Next. Let me recall some of the other things that we had before. And I said before, it doesn't mean 5 and 575 before in this class on Monday. So we talked about efficiency. So let me recall these definitions again. For a non-biased estimator, of theta in a problem where the regularity conditions are met, P of t or 1 over n e to the theta divided by the variance of t is called efficiency of the estimator t of theta. when you have an estimator theta hat 1n such that theta 1n hat minus theta times root n converges in distribution to normal with mean 0 and variance sigma square theta 1n hat. This is a constant, though you can see n on it. The quantity E hat 1n, which is equal to 1. Here you put theta 0 over ni of, sorry, 1 over I of theta 0 divided by that variance that you have there is called asymptotic efficiency. Of theta 1 and we say that the estimator theta hat 1n is asymptotically efficient if and only if that variance that you have there, sigma squared theta hat 1n, is equal to 1 over I of theta 0, which means that this ratio is 1. So that's one definition, definition 2, definition 3, and then a fourth and last. For two estimators, theta 1n hat and theta 1 and theta 2n hat of theta. So if we can use two different estimators, theta 1n and theta 2n, to estimate theta, then there is this quantity ARE of theta 1n hat towards theta 2n hat, which is the ratio of the two variances. It's called asymptotic relative. That's where you have ARE, efficiency. Of theta 1n hat 2n hat. Where here sigma 2n hat and sigma 1n hat are the variances that you have in this central limit theorem. Right? This is not y, but 1 over. And the big story for today is that when the regularity conditions are satisfied, and you have that the third derivative is bounded by a function that has a finite expected value, then you have this theorem, square root of n where the head is the MLE. So the MLE satisfies the central limit theorem if, on top of all the regularity conditions that we gave before, this extra condition is also satisfied, which means that the third derivative of natural log of f of theta in absolute value is less than m of x, and the expected value of f of x is finite, then the MLE is approximately normal. So it satisfies the central limit theorem as n goes to infinity, which is one of the justifications also why the MLE in general, it's very used, because you have the central limit theorem that is satisfied. Not just to know this variance, all you need to know this variance is to compute the Fisher information. And then if you're testing for a given value, which is theta 0, that's what you're going to put in there. And that's what is going to help you build your confidence interval or a test statistic, as we did in the other in 575. So, and this being the case, you can add this by the delta method, which is one of the things that we saw last time. Recall that here. For any continuous differentiable function g of x square root of n times g of theta hat minus g of theta 0 converges in distribution to normal with mean 0 and variance j prime of theta 0 squared over I of theta 0. This is what we called in 575 the delta method applied to a sequence that satisfies the CLT in this one. Just that the difference here is that here we are using theta, which is the MLE theta hat. I was hoping that we will have enough time to get into the likelihood ratio tests, but I guess after doing the examples, we just can't get in there.
We'll be in class next time, so I think that's better.
Surely, hopefully, everything works out well. In any case, the next class is going to be in person. Now, the thing is, it's not sure whether it's going to be me teaching it or not.
But you'll be continuing later when you arrive, right? Even though next class is taught by different instructor?
It's not sure yet. It's not sure if I will ever arrive or not. That's the point. That's the problem that we are facing now. There is a chance that it's not going to work for me. That's the problem. So that's the reason why this first week we decided with the agreement from the provost or whatever that I was going to teach it online. And if everything works out well, then yes, I will get back to campus and I will be teaching it from there. But if I'm not able to do that, then somebody else will take on the class. So it's really a very strange situation. So it's independent of the students and independent of me. I'm not the one deciding, not the university either. So I'm actually not in really no good condition to be teaching right now.
Oh, you have COVID?
In this country, some people say there are some, what do you call that? Let me just say I can't answer your question.
Okay.
All right, so I don't know if we should be doing another example now or perhaps try to introduce the likelihood ratio things. So give me a hint. What do you want? One more example or introduce the likelihood ratio test?
Is the likelihood ratio test on our first homework assignment?
No.
Okay.
The first homework assignment is just 3 problems, right?
Yeah.
Yes.
Yeah, I didn't put that on it because I was also under the impression that I might not get enough time to get into it. So
Then I wouldn't mind going over another example.
let's see. If I'm lucky enough, I will find one good example. Yeah, there is a strange problem here. Let's start this problem. We might not finish it, okay? It's possible we won't finish it. So we have, it's problem 6.214 of your book. And we say S square, we know what S square is. It's sample variance. Of a random sample of size n strictly larger than 1 from the normal distribution with mean mu and variance theta. We call the variance this time theta. Notice in the other problem, theta was mu, right? So now we call the variance theta. So theta, the variance is what we are interested in, and the mean mu is known. And here we say 0 less than theta less than infinity, mu known. So we have only one parameter. And it tells us expected value of S squared equals theta. This is true, we know this. The mean of the sample variance is the variance. And now the question is, what is the efficiency of S squared under these conditions? What is the MLE of theta? And then 3, what is the asymptotic distribution of theta? All right. So let's say, what is f of x theta in this case? That is 1 over 2 pi square root of 2 pi. And then sigma is square root of theta, right?
Yeah.
E to negative 1 over 2 theta times x minus mu squared. And then here, negative infinity less than x less than infinity. This is the support. Now one can check the regularity conditions here. For any different values of theta, this function will be different. So the support is the same for all values of theta. This does not depend on theta. All right. We can take the derivative. So what do we get here? Natural log of f of x theta, what is it equal to? It's going to be, can I just call all this a constant because it's canceling anyways when we take the derivative? So get natural log of that minus 1/2 natural log of theta minus 1 over 2 theta x minus mu squared. So this is it. And so you can take the derivative d ln of f over d theta. What is this equal to? This is minus 1 over 2 theta. And the derivative here is turning into plus 1 over 2 theta squared x minus mu squared. Right. Maybe we take another derivative. What we get here, minus, and a minus, that becomes a plus. So that's 1 over 2 theta squared. And the derivative here is going to be minus 2, and you cancel, so you get minus 1 over theta cube times x minus mu squared, right? Expected value negative. So I of theta is negative expected value of d2 ln over d theta squared f of x theta, which is negative 1 over 2 theta squared, and minus plus 1 over theta cubed expected value of x minus mu squared And what is this expected value equal to for the normal distribution?
That's the variance. So theta,
which is theta. So this is theta. So it becomes theta over theta cubed. So it's 1 over theta squared minus 1/2 theta squared. So that's 1 over 2 theta squared. And the expected value, what is it again?
mu.
It is theta. The expected value of S squared is
Oh, it's theta.
theta. So in this case, that K of theta again is theta, right?
Yeah.
So the asymptotic efficiency in this case would be 1 over this thing, which is just 2 theta squared. And now the other question these people are asking us is, under these conditions, what is the MLE theta hat of theta? So with these conditions, which means this, you want to find the MLE of that. How do we get the MLE in this case? Just write those things, take the derivatives and multiply. This is the log. That's the log we have. And we want to add these things, right?
Mm.
So MLE natural log of f of x theta is what you have. Natural log of 1 over square root of 2 pi minus 1/2 natural log of theta minus 1 over 2 theta x minus mu squared, and the log likelihood function is sum I from 1 through n natural log of f of xi theta. And that sum here is going to be this thing n times. So it's going to be n natural log of 1 over root 2 pi minus n over 2 natural log of theta, and then minus 1 over 2 theta sum of xi minus mu squared 1 through n. And so dl over d theta, when you take the derivative here, where you get is minus n over 2 theta. Derivative here is plus 1 over 2 theta squared, sum of xi minus mu squared. You set that equal to 0.
Can you erase the paper, please?
Yeah.
When you set that equal to 0 and solve for theta, you get theta, which is the MLE in this case, is equal to 1 over n sum of xi minus mu squared. And then you do the second derivatives test, okay? I'm not going to do this now, just writing down for you. Do the second derivative test. And then you end up finding that this is what the MLE is in this case, which is not S. It's not S squared, sorry. And say we ask, what is the asymptotic distribution of square root of n times theta hat minus theta? What do you think?
Zero comma 2 theta square by n.
Hmm. Normal 0 and what?
2 theta square by n, but let me check if that n should be there or not.
You can never have n
Yeah.
in.
Oh yeah, yeah. 2
You can,
theta square.
you can never have n in the limit. So
Yeah.
this is what you would have y. Why is that?
From the rule number, which rule was that? You taught rule number. The moreover from the delta method.
I of theta is 1 over 2 sigma squared. So 1 over that is 2 sigma squared. And 2 theta squared. Any questions?
Mm.
All right. I see you next time.
Thank you, Dr. Langla.
See you when.
Thank you, Dr. Langla. Have a good weekend.
Please complete the questions that we have there. It's not many of them, but don't wait till next week before you start looking at it. Then you'll forget everything.
Do you want us to email them to you like we did last semester?
Yes.
Okay.